Okay. Well, thank you very much for the introduction and for the opportunity to speak here. There's been much work on e-assessment, mostly at the undergraduate level, less so at the postgraduate level. And I'm going to talk about some experiences we've had at the Open University about e-assessment in mathematics at the MSc level. So let me first of all check that that's not quite good. Okay, that's good. Okay, so I should tell you a little bit about the Open University in case you're not familiar with it. It's Britain's distance learning university. It's been operating since 1969. Originally, it was University of the Air, with the idea being that tuition would be via television, but now it uses more of a blended learning approach. It's based in Milton Keynes, which is a city in between London and Birmingham. And it's very famous for where Bletchley Park, the code-breaking place, was located in the Second World War. That's inside Milton Keynes. It's got about 168,000 students, and we deal with levels all the way from opening for people without very much academic experience at all the way up to BSc, Masters, and PhD. Okay, so how do we work? Well, we have very high quality course notes supplemented by tutor marked assignments. That's what we call our assessments that are done within the course. And then we also have face-to-face and online tutorials. And there's a picture of a building from the Walton Hall campus in Milton Keynes. Okay, so e-assessment has actually had a very good history at the Open University. We were innovators in multiple choice objective testing a long time ago, from the 1970s onwards. We developed our own bespoke e-assessment system called OpenMark, which is available. I mean, it's a great system, but it did require professional programming in many instances, which is why I think it's not being used much today. Here's an example of an e-assessment question in OpenMark developed by Phil Butcher, who I have a great deal of respect for. This obviously is not in mathematics, but is in geology. But since 2008, we've had significant investment in the STACK system. We did consider other systems, including Newcastle University's number system, GEWIS from UWE, and MathCG from Brunel, but we decided to go with STACK, largely because it was integrated into the Moodle environment very easily. It scaled very nicely, of which I'll say a little bit more. And it was relatively easy to author questions, and it had a very powerful computer algebra system in the back end. So all of these features meant that we went with STACK, which at that time was at Birmingham University. So STACK is now an integral part of our e-assessment system at the Open University. I mean, it's quite staggering how much we actually do in STACK. These are the latest figures. We have about 1.3 million STACK questions annually are delivered by our system. And that translates to nearly 35,000 a week. And nearly 14,000 students are involved in STACK. And we have 6,500 different STACK questions. So all of these figures just show you how important STACK is. And it's been pioneered by many people and developed by many people within the Open University. But I want to highlight two of my colleagues, Tim Lowe and Tim Hunt. Tim Lowe is an academic mathematician, and he's pioneered and championed STACK within the Open University. And Tim Hunt is a technical developer, also a mathematician actually, and he's actually led a lot of the integration work with Moodle for STACK. And of course, Chris Angwin, you all know from the University of Edinburgh now. And the three of them won a teaching award in 2017 for the work they did on STACK. And I have to say that it's well deserved. So let me tell you a little bit about the Mathematics MSc up at the Open University. It's one of our first postgraduate courses, actually, long-standing. It's got about 500 students on it. And it's all done part-time. Students take about 2 to 6 years to complete 6 30-credit modules, mostly doing about 1 a year, although there's a tendency now for students to do more than that, especially younger students who want to complete their MScs more quickly. Our modules cover a range of subjects in the pure and applied mathematics, but we don't cover statistics in our MSc. And STACK and e-assessment generally is used principally in our 2 introductory modules, which are the calculus of variations and advanced calculus and analytic number theory. And that's obviously a pure maths course. I'm very interested to hear what the speaker that's going to follow me is going to say about using e-assessment in pure mathematics, because we do it to some degree in our pure maths modules at the MSc level. So the modules themselves are mainly assessed by a final exam. So here in the picture, you see the Alan Turing building at the Open University, where the Mathematics and Statistics School is based. And I'm pleased to say that I'm now working 1 day a week in this building, along with a couple of colleagues. So we're slowly returning to normality, very slowly. But I've been working at home for most of the year, last year and a quarter, as most of us have been doing. So I'm going to talk about our work with STACK in the module M820, Calculus of Variations and Advanced Calculus. As I mentioned, this is an introductory module of the MSc program. We get about 130 students taking it annually. And what we did is we developed 8 multi-question STACK quizzes, so they're Moodle quizzes. And we did it not for actual assessment of the students. The students are done by a traditional exam, though it's currently taken remotely via the internet because of the COVID situation. But the purpose of the STACK questions was to help the students to learn the material and to prepare for the exam. So we have about 30 STACK questions in total for this particular module. And we first developed them 4 years ago and again last year. So I'm not going to go into any detail on this slide. I merely explain that we do actually use STACK for quite a great deal of different problems within the calculus of variations at some level of sophistication, actually. And I'm only going to talk about one particular application, which is the use of STACK to teach people about classifying stationary paths through the Jacobi differential equation. That's what I'm going to concentrate on today. But as you can see, we've done quite a bit of work on various other aspects. So I'm actually going to give a crash course in the calculus of variations. I hope you apologize. I know it's 9 o'clock on a Friday morning, but I remember a time when I used to teach at that time, and students, I guess, still go to 9 o'clock lectures at some point. So I'm going to talk about the calculus of variations. It's a very important subject within mathematics. It's got a long history from the 17th and 18th century onwards. It has many applications, principally in physics, but also in biology, control engineering, economics, chemistry, and more. It's all about optimization. In fact, it's finding extremal or more generally stationary paths of functionals that are given by an integral of this form. The integral from a to b dx of some function, which typically is a function of the independent variable, the dependent variable, and its derivative. So that would be a typical calculus variations problem. Of course, there are many generalizations of that, and its applications in physics involve quite extensive generalizations of this basic idea. But the idea is that you find the stationary paths of this functional by solving the Euler-Lagrange equation, which is given there in front of you. This is typically a second order differential equation, in this case, an ordinary differential equation, but it's a boundary value problem, which makes it quite hard to solve quite often. And it's also typically nonlinear as well, which makes it even harder to solve. Now, what I want to talk about is the fact that we want to be able to classify the stationary paths. Suppose we've actually been able to solve the Euler-Lagrange equation with the right boundary conditions to get a stationary path. Well, we then want to classify it into whether it's a local maximum or a minimum or a saddle point. And that is typically a very hard problem. There are various approaches. And the one we particularly stress in the module is solving the Jacobi differential equation, which is an auxiliary differential equation that comes from the functional and also the stationary path. So I've written out in front of you the Jacobi differential equation. It's an initial value problem, while the Euler-Lagrange equation is a boundary value problem, but it's dependent, as I say, on the functional and also on the stationary path, and the coefficients of the Jacobi differential equation are given in terms of the functional and the stationary path by these formulae. And the important thing is you solve this equation with the given initial conditions, and then you look for what are known as conjugate points in the jargon. So if you're solving the problem on a sort of interval AB, then you're looking for points for which this function u, this solution of this differential equation, has zeros on the interval AB, excluding the left-hand endpoint where it obviously has a zero because that's given in the initial value. So if you can find a solution which does not have conjugate points, then you can use the Jacobi equation to classify the stationary path, and essentially you either get a minimum if this function p is positive, a maximum if it's negative, and if it changes sign, you'll get a saddle point. And so if you don't have you know, a nice solution to the Jacobi equation without conjugate points, and you have to do further analysis, but we don't go into that in the module. That's a whole order of difficulty greater. So now I'm interested to see how we went about devising a question within STACK to deal with the Jacobi equation. Well, one of the first things we did is we realized we had to restrict the type of functional being considered. Simply we need to make sure, first of all, that the resulting Euler-Lagrange equation and Jacobi equations could be solved, which of course is quite hard since they're normally nonlinear problems. So we chose quadratic functionals of this form, so quadratic in the dependent variable y and its derivative. So this is a typical problem, typical functional form, and it's sufficiently simple to be tractable, but sufficiently complicated to provide, to stretch the students and to teach the material in a variety of contexts. So we obviously add on boundary conditions. And as we developed the questions, we specialized these parameters, the constants A and B, and capital A, capital B, and alpha, beta, and M were all specialized as we developed the problem. So in this particular case, and it's not typically the case for most calculus variations problems, but for this particular one, the Euler-Lagrange equation and the Jacobi equation turn out to be the same differential equation, but they are different problems, although related, of course. So that makes things a little bit easier. So it turns out that the Jacobi equation and the Euler-Lagrange equation are both Euler equations in this case, which you can then transform in the usual way to a constant coefficient homogeneous equation, which we all know how to solve in terms of the auxiliary equation. It's a quadratic equation, basically finding the eigenvalues of the problem. And then we can solve it in the normal way. And because it's an Euler equation, it has a special form, the solution, as you can see. And I've written out the solution of the Jacobi equation there for you in terms of the parameters. Of course, you have to be a bit careful because for certain choices of the parameters, you might get a repeated root, for example, in the auxiliary equation. That might lead to a more complicated solution. And we tend to avoid, in the initial presentation of these problems, we tend to avoid the extra complexity which are given by these special cases. Okay. So one of the important things, as I say, is we wanted to restrict complexity, reduce complexity. So we restricted our parameter choices. And a lot of the work that we did involved trying to find good choices for these parameters that gave the problem sufficient bite so that students could learn from them, but didn't give a problem where students got bogged down in intractable algebra, which of course I think a lot of e-assessment has in the past at any rate suffered from. So what we did is we chose these number of parameters. We restricted the parameters, and then the key thing is that our problem was divided into essentially two cases, which were determined by whether the solutions of u of x, sorry, the zeros of u of x in the interval 1 to b, because a has been specialized to 1, satisfied this inequality omega log b is greater or equal to pi. It doesn't really matter what that inequality is. It just meant that we could flip between the cases very easily. So we either had no zeros in the given interval, in which case we had no conjugate points and we could apply the Jacobi test, or at least we had at least 1 0 and the Jacobi test failed. So we could switch between those cases and see whether the student understood. And if we did have no zeros, we had no conjugate points, then we could flip between whether we had a minimum or a maximum. And in this case, the possibility of a saddle point didn't arise because the function p of x didn't change sign in the relevant interval, being a constant. So it meant that we had enough for the students to learn the essential important learning outcomes of this problem. The Euler-Lagrange equation, as I said, is the same equation, though it's a boundary value problem. So it has the same solution functional form. And again, we chose parameters to simplify it, so it had a particular form. In particular, one of the things we did is we made sure that the value of the function at the left-hand endpoint was 0, and at the right-hand endpoint had this rather artificial functional form, so that solving the Euler-Lagrange equation turned out to be relatively straightforward. So there wasn't too much about algebra involved for the students. Okay. So here's the actual implementation, and this is simply the first question of a multi-part quiz. You can see, so we broke all of this rather complicated sort of process down into 5 separate stack questions, which are presented here, and this is simply the first one. And one of the things we found is that it was difficult to get the students to enter the results in a convenient form. So actually, rather than allow students the freedom to enter as they wished and then try to analyze the complicated expressions that might arise, given students' sort of imagination and creativity in that regard, we instead told them to enter it in a particular form so that we could analyze it simply and get down to the business of actually of the problem we're trying to deal with. So that's what we did. Now, I know that's not necessarily everybody's design choice, but it's what we decided to do. So here's an example of the feedback that we offered. We definitely provided extensive feedback on the solutions, including full worked examples based on the particular problem the students were asked to do. What we didn't do, and this was again a design choice, is we did not provide feedback that was particularly tailored to the solutions that the students had entered. That was simply going to be very complicated to do, and we made a decision that it wasn't worth the investment in time to do so. Now, I know that one of the great features of e-assessment is you can tailor feedback to student input, but we decided not to do that, and that's something which others may have different viewpoints on. So how did it all stack up? I do apologize for the pun. Well, it was extremely well received by students. So that's not always the case with the assessment in my experience, but in this case it was. And it's partly, I think, because we deliberately targeted it at revision. So students were using it, and I told them explicitly there was no such thing as cheating in this context. They could look at the answers before they even looked at the questions if they wanted. They could go backwards and forwards between the questions and the answers, was simply to see whether they were learning something from it. And of course they did, having that freedom. So they, as you can see, the comments from students, and these are just simply selected, but they were all pretty much all very positive about this. So as you can see, it was well received. And we did a statistical analysis of the results in our first year of operation. And it's quite interesting. Of course, this is all tentative. I mean, and it's very hard to make any real convincing statistical analysis of this type of thing with such a small group and so many confounding variables. So nevertheless, I did think we could do something. So what you see in front of you are the two groups of students. Those in blue, the blue circles, are those who interacted with the quizzes in some way during the course. That just meant they tried it once. So it's a pretty a limited idea of what interaction might mean. But if they tried the quiz once, we counted them as having interacted. The red students in triangles are the students who did not interact at all with the quiz. And what you see in front of you is actually a scatter diagram of the continuous assessment mark and the actual examination mark. And one of the things you observe, of course, is that there's a lot of bunching that takes place at the top right-hand corner of this diagram. And that really tells you that at the top end, at any rate, good performance in the continuous assessment is not a particularly good predictor of performance in the exam. Of course, in the continuous assessment, students have much longer and can consult many resources, which they can't do, at least at this point, in the 3-hour exam we set. So it's not surprising that the correlation between success at continuous assessment at the higher level and correlation and success in the exam was not very high. But nevertheless, we did conclude something from this diagram, which is that this was actually quite successful in helping students, not at the lower end or at the top end, but principally in the middle. The middle of the cohort were definitely helped by these quizzes that we put on. I have to say that you'll notice the red triangles are either in the bottom left-hand corner or in the top right. And I mean, we don't know exactly, but we surmise that these are the students who did not interact, or were those who did not engage at all with the module, and those who were, on top of everything and didn't see a particular need to interact with this extra material we provided for students. So there's definitely two classes of students who didn't interact. Okay, so I'm now going to talk a little bit about what are authoring tips. They're mostly common sense, but I hope that if you are involved in e-assessment authoring, that they are useful. Of course, like everything, they're more rules of thumb. They're not hard and fast, and they're suggestions, if you like. It's based on experience. I've been involved in this type of thing for about 15 years now, on and off, authoring questions myself. Most of these questions I designed, but I didn't actually implement. I did that with a colleague called Graham Erskine at the Open University. But anyway, these are just my take on things. Please feel free to disagree. So I put up a bust of Socrates because Socrates was one of the great educators of history, and so I think it's sort of appropriate here. So here are some comments I have on the design of e-assessment, some general principles. The most important principle that I have, and I've always realized this, I realized this very early on, was it's never a good idea to start from the question and derive the solution. It's always best to start from the solution and derive the question. You simply get better results all around. It's easier to randomize. It's easier to provide questions and solutions that students can do without all involving too much algebra or complicated arithmetic. In fact, in these problems, it turned out that that wasn't sufficient. Quite often the problems were just too complicated not to have some form of complication either in the question or in the solution or in some of the intermediary steps. So, although it's true that you should start from the solution and derive the question, it isn't a panacea by any means. The other thing I'd say is that it was very important to design this with someone else. So as I say, I designed these and Graham implemented them, but in fact, it was much more iterative than that. I would propose things and he would tell me why it wasn't a good idea, and I would propose something else and he would tell me why that, why that was a good idea or whatever. So it was a lot more, iteration and discussion involved in these problems. And I do recommend that people do it in collaboration with others. The other thing is, it's not a good idea generally to pattern match in these problems. You always check the answers, solve the problem, rather than to see that the answers fit a particular pattern. And that's my opinion. It's also important to solve problems outside the particular e-assessment system you're using first. So in our case, we solved the problems in Maxima first and explored outside the e-assessment system, outside STACK. And then we did the implementation. And the other thing I'd stress is that it's better to build from small and go up to big. And I suppose that's a sort of truism in most things. But it's certainly in this, we didn't try and solve all problems in one go, and we were not embarrassed to restrict what the problems that we were offering students in order to make them more tractable. The other thing I'd say is that they're listed here. It's hard to sometimes get some of these computer algebra systems to display things in a nice way. You can spend a lot of time trying to do that. So we only did it to a certain degree. We just sort of left the computer algebra system to do what it wanted to in certain circumstances. And the final thing I'll mention is, which I mentioned before, is that feedback is often the most time consuming. You might argue also the most beneficial aspect of this type of thing, but it is definitely time consuming and it's frequently omitted. Certainly we, by choice, decided not to tailor our feedback to individual student input, although we did actually offer extensive feedback in other respects. Okay, so just to illustrate what I'm saying, this is, when you deal with e-assessment, the first thing that a lot of people come across of any complexity is to solve second order constant coefficient ODEs. I think this has probably been implemented more times than any other problem, I imagine. But as you can see here, I've got a number of comments. The first thing is, if you're dealing with this problem, there are many possibilities for the right-hand side of a differential equation of this form, if it's inhomogeneous. And the various functional forms obviously affect the solution. And it's probably best to separate out the different functional forms, not to try and do something too complicated to begin with. So that's what we did. We actually separated out into different types of functional forms. These are typical ones that you see, which is actually easy to find particular integrals. So another point is that it's much better, as I say, to start with the solution and derive the problem. So often that meant deciding what this was a boundary value problem we were considering in our case principally, but here we've got initial value problem. So it's much better to tailor the initial values so that they are a nice solution rather than trying to present things in full generality, leading to quite complicated algebra. Like I say, it was often better to consider all the possibilities and choose randomly between them, rather than start with a problem and then try and analyze which particular problem you're in, which particular subcase you're in. So it's better to separate all the different subcases and work on those individually and then combine them into a general problem rather than take a more general problem and try and work out which subcase you're in. Finally, the comment I make is it's better to consider the generic case first. So in this case, if you have a second order ordinary differential equation of this kind, then the general solution, the complementary function, is given in general in terms of exponentials of this form, but there are obviously resonant cases that interfere, and so we generally avoided those in our implementation. So these are the sort of problems that you encounter whenever you do e-assessment, and we encountered them in what we were doing, which was obviously a little bit more sophisticated than this. But the general principles that I outlined on the previous slide, I think apply quite generally within e-assessment. So let me stop there and thank you very much for your attention. These are 2 references to 2 papers that we published on this work, and I'd be very happy to answer any questions. And thank you for your attention. I hope I didn't go over time because I wasn't watching time at all.
Yeah, thank you very much, Ben. I think we can appreciate Ben using the reactions on Zoom. Because we didn't do so well on time, maybe I would just give you to look at the questions on the Moodle side. But I think there was one question maybe which refers to your slides, maybe from Ingodan, and it was in question 2 in your example, based on the student is it based on the student input from question 1?
I'm sorry, I didn't understand that. Beg your pardon.
Sorry.
Which slide was that?
Yeah, the question was, is question 2 in your example based on the input answer from question 1? Like, is it a
I see. So when you see this, let me go back here. For example, this thing here. Yeah. Here. So it's certainly the case that no, it's not the case. What we do is we provide a problem that develops in complexity. And the idea is that students go through it in order, in principle, but they can move between the different parts. But the different parts are not dependent on whether the student got it right in the previous parts. We didn't do anything sophisticated, sort of programmed learning, as it used to be called. We didn't do anything like that. No, it was simply the problem was sufficiently complicated that dividing it up into different steps was sensible. And we did it in that way.
Okay, thank you. I think there are more questions on the Moodle side. I hope you find time to answer them. We'll be also looking forward for the answers.